Test, test, test. Good? Great. All right. No, just one. Just make sure. You just need to switch it out every time. Okay. Now you should be good. But those are the two ones just in case. And I think they are looking for another person.
All right, cool. Hey guys, can everyone hear me? No. Can you go? Hello? Can you guys hear me now? All right, cool. Ooh. I just put this in my pocket, I guess. All right, can everyone hear me? All right, cool. I love the enthusiasm. Whoever's over there yelling, I love it. Let's get started. All right, so the couple things I just want to talk about really quick. So your final exam, like you just said, you're only going to have 50 minutes. For my ACS exam, I did the math based on the amount of time I have and the amount of, oh, it's going to be sideways. And now it's not going to be sideways. All right. So the amount of time I have divided by the questions I have 1.7 minutes per question. I did the same calculation for you guys. You have 1.4 minutes per question. So it's really the same thing. The ACS is standardized, so there's no way to escape it. Dr. Hernandez is actually doing you guys a really big favor by helping you out with some of those questions. So, yeah, all right. I wanted to say one more thing, and I forgot, but let's start. Okay, so we're going to start with Chapter 10. If you've been coming to SI, you've heard me say that, but we're going to start with Chapter 10. Then we're going to move on to the Chem 1B packet, and I'll be, going through the pages, skipping where I want to skip and working where I want to work. And then same thing with this one. Like I said, tomorrow I will post all of the answers to all of the questions on both of the packets. Answers to this, if you want the answer while I'm working on it, take a picture of the screen or just write it down as we're going through. Can everyone see that? And can everyone hear me? All right. So determine the molecular geometry of nitrate. What do we have to do first? Yeah, we have to draw the Lewis structure, and then if we go back to Chapter 9, we have to draw our skeleton and come up with valence electrons and all that good stuff. So when we talk about valence electrons, how many do we have coming from nitrogen? 5. How many from oxygen? How many oxygens? And this is an ion, right? So it's a negatively charged ion. Do we gain an electron or lose an electron? Gain. So plus one more gives us 24. How many in our skeleton? 6 in our skeleton, that leaves 18, and that's how many it'll take to complete octet, right? So once we complete octet for this structure, for the oxygens at least, we are out of electrons. What's wrong with this structure the way it is? I'm sorry? Awesome. So how do I give it a full octet? Yeah, we're going to delocalize. Does it matter which oxygen? No, we're just going to take these electrons from this oxygen and turn it into a double bond. I'm going to start using pencil so I can erase so it doesn't look like oxygen has a bunch of stuff. So that's what it should look like. What is the molecular geometry of that nitrogen? So I heard trigonal. Trigonal what? Planar, awesome. And we know that because 3 electron groups and no lone pairs. So if you go to your chart, That's what it would say. Remember that you need to memorize that chart, and you're just going to have to be able to pull it out of your head. The people who came to SI today, I told them a goal for everyone should be by Wednesday. You shouldn't have to really look at anything. You shouldn't need any help outside of your brain by Wednesday, meaning if someone said, or if the question gives you 2 electron groups, you should know what shape that is. If it gives you 4 electron groups and 2 are lone pairs, you should know what shape that is very quickly without having to check the book, because your test is on Friday. All right, so moving on, carbon tetrachloride. We all agree it would look like this, right? And at this point, octet would be filled for everything, right? So what is the molecular geometry of this shape, or of this structure? Tetrahedral, nice. While we're working on it, what is the hybridization of this nitrogen? sp3 or sp2? Yeah, it's going to be sp2 because how many electron groups do we have? 3. And then what's going to be the hybridization of this carbon? sp3, yeah. When we move on to sulfur tetrachloride, we would expect the same thing, right? But that's not what happens. The difference, what is the difference in carbon tetrachloride and sulfur tetrachloride? Yeah, we have carbon in one case and sulfur in the other case. And sulfur can have an extended octet where carbon cannot. Excuse me, carbon has 4 valence and sulfur has 2 valence. So at this point, this structure has 2 extra valence electrons. And those are going to go on the central atom. Now when we look at this, it has how many electron groups? 5 electron groups, and one of those electron groups is a lone pair. So what is our molecular geometry? Seesaw. And what is our hybridization of this sulfur? sp3d. I'm sorry? Can I explain the seesaw? Meaning, like, what does it look like? Or so seesaw would look like this. So that triangle, this triangle right here, you guys will learn as you move on in chemistry, that solid triangle means it's coming out of the page, and that line means it's going into the page. So when you see a seesaw, remember, we want to see these things in 3D, so these kind of notations will become necessary for you to learn eventually. But we see that this lone pair is right up here. We have 2 chlorines going right out to the side, and then one coming towards us and one going away from us. And that's this part of the seesaw, and then this is where you would sit. It literally looks like a seesaw. So, all right, so I think that was good practice for that, so I'm just going to move on. You know, this is from the book. But, yeah. What's the difference between this and all the other ones we just did? It's organic. But if I draw it like this, what do you notice to be a difference? Yeah. It has 2 central atoms. So this kind of question would have 2 answers. You would have to tell me the molecular geometry for carbon, which would be what? Tetrahedral. And then you would have to tell me the molecular geometry for oxygen, which would be what? Yeah. It'd be bent. If you did the structure out, you would see that there's 4 electrons left over once you make your skeleton, and they all go around the oxygen. And what I meant to say earlier is the ACS is designed to test what you know. So that sounds dumb, but you should look at a question, and honestly, within 30 seconds, you should be able to answer it. If you can't answer it in 30 seconds, you don't know it. It's pretty harsh, but that's the reality. I've been studying for my organic ACS. If I don't know the question, I can't waste time on it because I have 20 other questions I need to get to in like 10 minutes. You don't know it, you need to move on. You can come back to it if you have time, but that's how it's made. It's made 40 questions, 50 minutes. It doesn't give you time to think hard. It gives you time to just think. Do you know the hybridization? No? Too bad. Go to question 4. So think of that while you're studying. I should be able to answer these questions in like 45 seconds, and I should be able to move on. Because he says you have about 1.4 minutes per question. That's not considering the time it takes you to read and think about it. I mean, that's 30 seconds right there just to read a question. You don't want to be reading it too fast and miss stuff. So, all right. What is the difference between polarity in chapter 9 and polarity in chapter 10? Yeah, awesome. So that's 2 for 2. Polarity in chapter 10 is determined by the entire molecule. Polarity in chapter 9, we really only looked at the bonds themselves. So when we draw sulfur difluoride, how many valence electrons do we have from this sulfur? 6. And from the fluorine? And there's 2 of them, so 14. That's 20. Then how many in our skeleton? 4. That leaves us with 16. How many to fill octet on the fluorines? 12. That leaves us with 4. And those go where? This kind of looks like what that we're all very, very familiar with. Water, yeah. You would have oxygen right here, hydrogen right here, and 2 lone pairs on the oxygen. So it's similar to it, but not really like it. Is this bond polar, this sulfur to fluorine bond, is it polar? Yeah. And so if we're looking at this in 3D, this is what it really looks like. So if you have polarity this way, would you say that this structure is polar? Think about these vectors. Are they canceling out in any way? No. So if they're not canceling out, they're going to do what to each other? They're going to add up. And they're going to have polarity this way. So this is polar. Is it polar? Yes. Carbon dioxide. If you see CO2 on a page and you don't immediately see that in your head, you probably need to study more. This is the most basic Lewis structure. And it's one of the only examples of a linear structure. So if this isn't familiar to you, you haven't studied that table enough. I'm just trying to be honest with you guys. So we look at this. Is there polarity along the bond? Yes, there will be. Oxygen steals electrons from carbon because it's more electronegative. So we would see equal magnitude bond polarities, but facing complete opposite directions. So is this structure going to be polar? No, this will not be polar. And we didn't talk about it. This is how it would also look in 3D because it's linear. So we would just expect to see it on one plane just as a straight line. So let's move on to NH3. Not polar. All right, so this is NH3. And we have 8 valence electrons, 5 from the nitrogen, 3 from each, 1 from each hydrogen, equaling 3. We have 6 in our skeleton, 2 left over. They're going to go on the nitrogen, right? So what is our molecular geometry? We have something with 4 electron groups, and one of them is a lone pair. Awesome. Trigonal pyramidal. So I'm going to write that. Anytime I write tri, that's just a shortened version of trigonal. So tri-pyramidal. So what this is really going to look like in 3D now, this bond is polar. So this is what it looks like in 3D with polarity vectors. Do you see any of these vectors canceling each other out? No. No, none of them are canceling out. So that means they're all going to add up. And this is actually another example of a polar molecule. Who was at SI today? What was the page number? Page 441? I think it's called table 10.2. I believe page 441 is the page. Also, page 464 and page 465 are very important, so you might want to write those down. 441, 464, and 465. On page 441, there's a chart, and it says, it talks about certain configurations when you have equal bond polarity. So, for example, we have equal bond polarity, magnitudes of bond polarity. So in that table, it says when it's linear and you have equal magnitudes of bond polarity, it is nonpolar. So if you understand that chart really well, you can be like, oh, it's linear. Both of these are oxygen. This is carbon. It's not going to be polar. And then it talks about how when you have trigonal pyramidal and all the magnitudes are equal, it is polar. So that will actually help some of you out, take some of the thinking out of it and just put some of the memorizing into it, which is sometimes easier for us. Any questions about polarity and molecular geometry? I will keep these pages up here for you guys to take pictures of after if you didn't get everything and stuff like that. All right. Now this is pretty much the same thing, hybridization of BrF3. I'll just help you guys out to speed this along. That's what it's going to look like. That's what its Lewis dot structure will look like. So when we look at that, we have, let's talk about shape really quick. We have 5 electron groups and 2 are lone pairs. What's our shape? T-shape, yeah. I mean, it looks like a T. T-shape. Now, 5 electron groups, what is our hybridization? sp3d, I believe someone said? Yeah, so, end of question. What's the hybridization? We draw the structure, we draw it correctly, we count electron groups, we make a connection to hybridization. All right, this, I drew a little different for you guys. So this is just formaldehyde, or acetaldehyde, whatever, it doesn't matter. So CH3 connected to COH. Ooh, I want to say that's right. All right, so we're going to call this carbon 1, and we're going to call this carbon 2. What is the hybridization of carbon 1? sp3, I heard. And what's the hybridization of carbon 2? sp2. Oh, sorry, guys. Why? Because carbon 1 has 4 electron groups, and carbon 2 has 3 electron groups. Now, for those of you that still don't understand how we're figuring out hybridization so easily, this is a way I like to think of it. All right, so when we have 2 electron groups, what's our hybridization? sp for 3, 4, 5, 6. All right, awesome. So some of you might be wondering, how are people just like yelling that out? How do they know it? SI must be amazing. Asad must be amazing at his job. All right, this is how they know it, because this is what we talked about. This is something I came up on my own, just by sitting there studying forever and trying to pass my freshman year of college. All right, so when you have a number just floating in space, like let's say 4. 4 is to the first power, right? Because 4 to the first power equals 4. Does that make sense to everyone? So you can think of these numbers, these letters, s to the 1 power, p to the 1 power, s to the 1 power, s to the 1 power, s to the 1, d to the 1, s to the 1. Now all you do is you count the numbers on top. So 2 electron groups, 1 plus 1 is 2. 1 plus 2 is 3. 1 plus 3 is 4. 1 plus 3 plus 1 is 5. 1 plus 3 plus 2 is 6. That's pretty much exactly what the chart says. It just doesn't put it, out that clearly. So if you're curious, if you have 5 electron groups and you're like, man, do I have the right hybridization? What do? If I have S, I have 1, P3 plus 3 is 4, plus D, 1 is 5. So hopefully that makes sense. It makes it a little bit easier for some of you. And if you don't believe me for some reason, you can use the chart and do the same kind of math. All right, so this is already set up, same kind of thing. Carbon 1, carbon 2, what's our hybridization? sp2, we want to double check that. We have 1, 2, 3 electron groups. 1 plus 2 is 3. Is carbon 2 going to be any different as far as hybridization? No. Any questions about hybridization? No. All right, so I said today in SI, he said it Friday in class, you're going to have to know these. Every single semester for the past 2 years, on the final exam, he's asked one question about the orientation of the antibonding and bonding p orbitals. It just happens. And if it doesn't happen, oh well, but if it does happen, you'd rather be prepared for it. So, can anybody remember what orbital this is and whether it's bonding or antibonding? So they're all going to be pi. They're all going to be p. It's either going to be antibonding or bonding, and z, x, or y. Yes? Okay, awesome. Yeah, so that's a good way to start. It's not bonding, so this is antibonding for sure. Do you know what plane it's on? X, Y, or Z? Z, yeah. Someone helped you out. They yelled it out. This is the antibonding PZ orbital. So we go down here and, you can see this is antibonding pretty clearly, so you must think that these are bonding, right? So this is going to be bonding orbital. This is going to be bonding. Does anybody know what Cartesian plane this is on? I heard it over there. Someone said X. And let's guess. What's the only one I haven't asked you about yet? Y, yeah. This is Y. Sorry. So page 464, page 465 is where you'll find these. Page 464 is these two, antibonding and bonding, these two up here. 465 is this one, antibonding and bonding. In the second half of 465, for some reason I can't remember what's on it, but I remember it was important because I told you guys that it was important earlier. What's up? For this, to get the information for this, I would just go to the book, 464, 465. It explains it. I'm pretty sure these are all pi. Or you can go to his slides where it has the pictures pretty clearly there too. All right, so pretty much wrapping up chapter 10, we talked about bond order. So determine the bond order and tell me whether it's para or diamagnetic. We are skipping this one. We are doing this one. So what is more... I don't know what I was about to say. So when we're doing this, we have to set it up a certain way, depending on what elements we're looking at, right? Because we can either take the BCN track, which is pi, sigma, or we can take the ONFE track, or the OFNE track, which is sigma, pi, sigma. Which orientation are we going to use of the molecular orbitals? I'm sorry? The nitrogen one. And are we starting with, in our 2p orbital, are we starting with pi or sigma? Pi. Yeah. Who remembers how I told you guys to remember it? ONFE. These are all to the 2. So it's always 2s sigma non-bonding. So that is the same over here, 2s sigma non-bonding, 2s sigma. Can you guys see that? What's the first one in the p orbital when you're dealing with oxygen, nitrogen, or, I'm sorry, oxygen, neon, or fluorine? Sigma, yeah. Go sigma, pi, sigma, right? The last two never change. These last two, these antibondings never change. And then that means this one has to be pi, sigma. Antibonding. So what I would suggest for you guys to do is remember the 3 that are paired together. Remember BCN, and remember OFNE if you remember BC-NOF, BCN are right next to each other, but whatever. When your group starts with oxygen, your 2p orbital starts with sigma. They both look like circles. That's the best way to memorize it if you want a trick. If you're not really expecting a trick, then just straight up memorize it. But besides, if you're looking for some sort of trick to memorize it, that's the only thing I have. All right, so we're going to be using this way. So let's set it up. We have 2s sigma. We have 2s anti-bonding sigma. So this is going to be 2p pi. It's going to be 2p sigma. Yes, ma'am. Then we're going to have the pi again. 2p pi anti-bonding. And then 2p sigma anti-bonding. All right, so when we're talking about carbon, how many valence electrons is it contributing? 4. So carbon, 4 valence. And then nitrogen is contributing how many valence? 5. So nitrogen, 5. So 1, 2, 3, 4, 5, 6, 7, 8, 9, right? But this is an ion. So we would add, when it's negatively charged, do we gain an electron or lose an electron? Gain, So now to determine the bond order, what do we have to do? So we do half of bonding minus anti-bonding. So bonding is 1, 2, 3, 4, 5, 6, minus 1, 2, 3, 4. 3, 1, right? And then is this paramagnetic or diamagnetic? Diamagnetic. And what's the definition of diamagnetic? Sorry, guys. Everything is paired, and so what would be the definition of paramagnetic? Yeah, only at least one electron is unpaired. Yeah. Oh, I got them from nowhere. I made that up. Yeah, that's what I was thinking. I'm losing my mind a little today. Yeah, all right, so this is our only, thank you, Bert. This is our only anti-bonding that's filled. This is actually not a non-bonding orbital. It's only these two that are non-bonding, so this is part of the bonding. So it should be 1, 2, 3, 4, 5, 6, 7, 8, minus 2. And that would give us what? 3, yeah. Thanks, guys. I make mistakes too, so always pay attention. Yeah, it should still be diamagnetic because we still, diamagnetic, we still use the same amount. All right, so this is a question I asked. This is a good question to ask. If a molecule is bent, what is its hybridization? There's 3 possible answers to this question. There's 2 possible answers. The correct answer being its hybridization, or it not being possible, needing more information. So if a molecule is bent, what is its hybridization? sp2? Does anybody else have? So think of it like this. You're going to have to pick this off a test. And there's only going to be 4 choices. And if you've seen a scantron before, you can only bubble in one answer. So let's say this says sp2, this is sp, this is sp3d2, and this says unable to determine. What would you guys pick as the answer? D. Why D? Yeah, there's not enough information because we can have bent with 3 electron groups, 1 lone pair, or 4 electron groups, 2 lone pairs. So if I tell you that this structure is bent, how many electron groups are there, what is a hybridization, your response should be, I don't know, because I need more information. What about linear? SP? Okay. Do we see linear in more than one place? Yes. What's the other hybridization where linear is present? I'm sorry? If there's two lone pairs and what? For what, octahedral? If we have tetrahedral with two lone pairs, that'll give us bent. Linear can show up if you have 2 electron groups or 5 electron groups. It's also not enough information to just be like 2 electron groups, 5 electron groups, because it can show up in more than one place. Now, when we talk about trigonal pyramidal, where's the only place we see that? This should be the easiest stuff I'm asking about this chapter. A student just asked Dr. Hernandez if he would be providing this chart, and his response was, you don't know it. So questions will be asked about it. It was talked about the second lecture of this chapter. I mean, there's stuff that's so much harder in this chapter. These geometries should not be the difficult part. If you know it and you're just not yelling it out and like you know on your own, that's cool. That's good. If you don't know it, you need to study this stuff. Everything stems from this. Everything we just did, I don't know how you guys knew the answer because you don't know this. So yeah. Final is going to be harder than it has been for classes before you guys. You guys are taking ACS and you're taking this chapter 10. So, be prepared for this stuff. Trigonal pyramidal, a hybridization can be SP3. Seesaw, it can be SP3D. And square planar, it can be SP3D2. And then these are cannot determine. So that's what I prepared, like specifically for chapter 10. And now I'm going to move on to this final exam, this really large packet final exam practice for Chem 2041. All right, so I picked this review. I got it from another SI leader. I picked it mainly because of the first 3 to 4 pages. It's all concepts, and it covers almost every conceptual thing that we've talked about in this class. So I thought this one was really good. When I post the answers up, you can check over. We're going to go over it now, but if you don't understand something, you can see it with the answers. So when we're at the bottom of the electromagnetic spectrum, so when I'm talking lower energy, what is high? I'm sorry? The wavelength, yeah. And so when you think high, you want to think large. The wavelength is larger. And what's low? Frequency, yeah. So frequency. The opposite, on the high energy side of the electromagnetic spectrum, what is low or small? Wavelength, and we have a high frequency. So the uncertainty principle, Heisenberg's uncertainty principle, it was the change in x times momentum is greater than or equal to h over 4 pi. And this was used in this, I don't know. This was used recently, and it was used as an equation, and there's also a concept behind it. So you might want to go back and read up on some of those concepts, those problems that are more than just an equation. What is n equal to? Awesome. The principal quantum number? Quantum number. What is L equal to? Do you guys remember that? Angular momentum. I'm wasting my time. So L is equal to the angular momentum number, and ML is our magnetic quantum number. Do you guys remember what MS is, even though it's blank? Yeah, it's our magnetic spin. And we always have one spinning up and one spinning down. When L equals 0, what kind of orbital do you have? S. When L equals 1, P. When L equals 2, D. And when L equals 3, it's an F orbital. Have a general idea of how these orbitals look. I mean, like I said, don't spend hours memorizing little bubbles, but have a general idea. S is 1 sphere, P orbital is 2 spheres, D is 4 spheres, that kind of thing. Hund's rule. I think this is easier to show than explain, but I have 2 electrons. I'm going to fill this box up once and then fill that one up once. So Hund's rule is, feeding everybody before anyone gets seconds kind of thing. So everyone at the table eats before this guy can get seconds. All right, moving on. Aufbau's principle. It is how the orbitals fill up. Just based on their energy. Dr. Hernandez prefers that you guys know it based on the rain method. And I believe a lot of you are very comfortable with that. That is something that I strayed away from when I was in class just because I'm weird and I do stuff differently. But it's easy. A lot of you are comfortable with it, so keep using that to know Aufbau's principle. Pauli exclusion's principle is no 2 electrons in an atom can have the same 4 quantum numbers, whether they're on the same principal level or in the same orbital or even, any of that. Something will always differ about its quantum numbers. Coulomb's law, if you remember that, E equals charge 1 times charge 2 over the distance that separates them. Like charges repulse and opposite charges attract. I imagine this is blank because the best way to understand it would be to look at your book and look at those graphs that show the relationship between radius and potential energy. So I would suggest if you're worried about Coulomb's law to just check that out. I think that was maybe 1 chapter ago. This should be easy. Don't forget, I know this one, so this is from a different class, so it only has copper and chromium, but just remember all of those exceptions. And it's less about remembering that gold and silver were one of them. It's more about understanding why they're exceptions. And you don't need to memorize them individually if you understand why, because then you can just look at the periodic table and understand where these exceptions are found because you understand why they're found. Effective nuclear charge is Z minus S, where Z is the number of protons and S is the number of core electrons. Remember, you guys are taking a standardized test. Slang is not tolerated in the standardized world, so they're not going to refer to this. If they give you S they're not going to say core electrons. They're going to say charge screened by electrons, they're going to say something crazy. They're going to say something that would come out of the book, something standard, that when they say it, everybody from every part of the world understands it. So if you use slang to kind of understand some of these things, try to fix up the vocabulary. So if on the standardized test they specifically refer to something the scientific way, you're still comfortable with how they're referring to it. We just talked about that. Atomic radius, you guys know it increases that way, with fluorine being the smallest. I think it's Ra on the bottom being the largest. Cations are smaller than their neutral atoms, and anions are bigger. And just think about it. A cation has more positive charges or more negative charges? More positive charges. And where do you find the positive charges? On the inside or floating around the outside? On the inside. So if you think about this, if you have 4 minuses floating around, and 5 pluses in the middle, it's going to be easier for 5 things to pull in 4 things than it is for 4 things to oppose 5 things. So that's why we see cations, which are much more positive, are smaller. All right, so. I'm going to kind of save this stuff for you guys to go over and read, but this is our ionization energy trend. This is our electron affinity trend, or electron negativity. Oh yeah, electronegativity also has that same trend. And the metallic character is that way. This is the important one I would take away from it. Fluorine is the most electronegative. So there's actually a question on one of these practice tests where it's hydrogen with 5 different halogens. It doesn't give you any values. It doesn't give you anything. And all these halogens are right next to each other. You would think they would have, you would think they would have high electronegativities. But since fluorine is connected to one of them, you just know that's the most electronegative because you just know that fluorine is the most electronegative. All right, so basic stuff like this is probably a little bit more for Chem 1A when you learn this, but it's still important. Group 1 are alkaline metals. Group 2 is alkaline earth metals. If you take out the word metals, Group 1 only has 1 word and Group 2 has 2 words, if you need to remember that. Group 7s are halogens, and Group 8 is the noble gases. Everybody wants to be like them. In an ionic bond, they're not shared. It's a metal and non-metal. In a covalent bond, they're sharing them, and it's between 2 nonmetals. Formal charge, the rules on that. This is important. Oh, sorry. It's important, nothing. The exceptions in octet. So boron has 6 electrons and its octet's full. Beryllium is 4 and its octet's full. Hydrogen is 2 and it's full. And then row 3 can have an expanded octet. So anywhere in chemistry, Chem 1A, Chem 1B, where there is exceptions, I would assume that that's important to go back and maybe look at. Breaking bonds requires energy. If I wanted to break this pencil, I would have to put energy into it, right? So if you ever get to a question, just pick up your pencil and try to break it. And it'll take energy, and you'll understand that breaking bonds takes energy. Forming bonds releases energy. That's a favorable process. I'm not going through that again. That is there for you. The answers will be there. If just having that page is easier. One thing I do want to talk about when you guys are looking at this on your own, this might confuse people the way it's set up. It's just 2 bonds, 0 lone pairs. 3 bonds, 0 lone pairs. 2 bonds, 1 lone pair. That's how it works. So I'll let you guys figure that, deal with that on your own. All right. This page for you guys stops right there. So when you have a single bond, how many of those bonds are sigma bonds? 1, and that means there'd be no pi bonds. A double bond, how many are sigma? And the other one is pi. When you have a triple bond, how many are sigma? And the other 2 are pi. And I go to the lab and I'm just really good at chemistry and I make a bond. 2 structures that have, X and X, and there's 74 bonds in between them. How many of them are sigma bonds? And what are the rest? Pi bonds. So that's a really extreme example of how sigma bonds and pi bonds make up multiple bonds. All right. All of this, just cross it off like that. This is intro to organic. Same thing. We're not talking about any of this until you get to this part. Boyle's law. Don't neglect Boyle's law. So what you want to know from this is the same thing you wanted to know when you were preparing, is that this is the equation and that the other variables are constant. This is the relationship between pressure and volume, and that the variables that aren't there are constant. They could simply ask, in Boyle's law, what's a constant? And A is P, B is V, C is T, and D is there's no constants. I mean, that's a 10-second question. You write Boyle's law, you're like, what's not there that's in the ideal gas law? Those are one of the constants. And you move on. So that's why on the ACS you only get 55 minutes for 40 questions. But then on Dr. Hernandez's test, he's going to give you the same amount of time and give you 15 questions. So that should speak volumes about the test. What you guys have already done 3 times this semester, you got the same amount of time, but you only did 15 questions. They're going to give you that time and give you 40 questions. The questions cannot be as difficult. It wouldn't make sense. So just think about it like that. The test should be easier than what you guys are used to. Charles' law, same thing. Know what the equation is and what the constants are. STP variables. This is very important. When they give you a question and say at STP, you don't have any of this, right? This is supposed to be in your head. So STP means 22.4 liters, 1 mole, 1 atm, and 273 Kelvin, which is also 0 Celsius. All right, so let's start the fun stuff. So the SI leader before me, she actually wrote on this one, so you guys will have some explanation on this one. Please remember, I did not make these, so if you have any problems, if there's typos, if the answer is wrong, I'm not the person to attack with the angry mob. I'll try my best to fix it. If you can put a picture of it on Facebook, I'll take a quick look at it and see what I can do. But, I mean, if you're confident in the concept, and you know that it's not correct on the test, you're probably right. Because you're studying it currently, and, you know, if you think it's wrong, it probably is wrong. All right. Okay, so choose the electron on average that is furthest from... Oh, I could have done that the whole time. Choose the electron that is on average furthest from the nucleus. What is the closest orbital to the nucleus? S, so 1s. So what would be the furthest? The largest number and the largest letter. So we go and try to find that, and we see, yeah, an electron in the 5f orbital. Of the following transitions in the Bohr-hydrogen atom, which is responsible for the absorption of the greatest amount of energy? Now this is important. We have absorption and emission. So when do we emit energy? When we go down. And when do we absorb energy? Yeah, when we're going up. So we want to absorb, which means we can't go down because we would emit, and we can't go down because we would emit. And then now we just want to find what would be the largest jump, because it's asking for the greatest energy. Do you guys remember how this Bohr hydrogen model is set up? One, two, three, 4, 5, 6. So that is a very poor drawing, but you get the idea. The gap between 1 and 2 is huge. It's the largest gap between 2 successive levels. So what do you think would be larger, from 3 to 6, 1 to 4, or 1 to 6? 1 to 6, yeah. Which set of 3 quantum numbers cannot occur together to specify an orbital? One more thing I want to say about your guys' final exam. Dr. Hernandez was like throwing out general topics that are going to be covered, and I saw a lot of people like furiously writing, trying to get everything he was going to say. You need to know everything. It's not like what he was saying is going to be focused on. He was just trying to name the concepts and like remind you of them. Like when he said quantum numbers, some people are probably like, oh crap, like quantum numbers is a thing that we need to know. So he was just trying to remind you of them, but he was not giving you a specific list to study or focus on. You literally need to know everything. And you're not going to get asked everything. which is why it's important to know everything. So, all right. When n is x, what can L be? Yeah. So it would be like x minus 1 to 0, right? And then what is ML? Yeah, positive L to negative L going through 0. That's important. We have to include 0 in those numbers. So we go through this, and we see this one pops out to me right away. The N and the L is the same thing. Is that possible? No, so that's wrong for that reason. Give the value of the quantum numbers N and L for a 3D orbital. Excuse me. So what is our N? That's pretty easy. 3. So get rid of this, get rid of this, get rid of this. And that's how you're going to want to approach this test. He said that sometimes you won't know the right answer, but you'll know the other 3 are wrong. So if you can cancel stuff out, make it easier for yourself. This is easier to pick from than 5 answers. And then pretty much when L equals, when we have a d orbital, what does L equal? 2. So for some reason you only know what L equals 0 is, you'll know that this is wrong because this would be 3s. And since there's only 2 choices, you would just have to put all your faith in the fact that you know all of the other ones are wrong, as opposed to knowing which one's right. Which of the following orbitals is impossible? So which one doesn't make sense? 1p, yeah. We only have 1s orbitals. I'm skipping 6. It's just a constant. It's how does this affect it? You plug all of them into the equation and you find the one that gives you the best answer. So that's not. Let's go with that. All right, so let's go to number 8. Which group in the periodic table contains elements with valence electron configuration of ns2np1? So where do we find 1a, 2a, 3a on the periodic table? Do we find it on the left or on the top? On the top. So ns2p1 would correspond to which column? 3, yeah. You guys see this? How it says 6? Write this next to the problem. Because when I go to number 8 on here, it's not the same thing. This is what I'm going to post for you guys to get the answers. Number 8 is not number 8 on this. So I wrote a number 6, so you guys will know to go to number 6. So I went through this and tried to realign all the questions so it made sense. All right, so this question, let me cross out these words. So I should have kept this word. It says electron. So electron configuration of an element is argon, 3d10, 4s2, 4p3. Or 4s2, 3d10, 4p3. What is the charge of this monoatomic ion? Meaning, this is its electron configuration. Go find it on the periodic table and tell me what its charge is. So ns2, 4p3 would put us where? So just like we did the last one where ns2, np1 put us on 3a. So where will ns2, np3 put us? At 5a. You go to your periodic table. I have one somewhere. You go to 5a. What is the charge of everything in here? -3. Moving along. What is the maximum number of orbitals that can be accommodated in the energy level which has n equals 4? What's the easiest way to do this? When they just want you to find subshells for an entire principal level. N squared is the easiest way to do it. What if they said, tell me the amount of orbitals at n equals 4, L equals 2? Yeah, you would use 2L plus 1. And that would give us, what, 9? Oh, that's wrong. Oh, wait, that's right. Oh, that's so wrong. Oh, my God. Sorry. So 2L plus 1, where L equals 2. So if you took Dr. Hernandez this semester, he kind of tricked you with that. In the book, they just say n squared. You can use it. In his slides, they say n squared because they don't specify an L orbital. But on the test, he specified an L orbital. So be careful for this on the standardized test. You might get something as simple as this, how many in n equals 4, but just make sure you're reading it, and they're not specifying an L orbital as well. Okay, in which pair is the first member larger than the second member? So what do we know about cations? Are they smaller than their corresponding? Yeah, and then anions would be larger. All right, so we look at this, Li plus and Li. Is Li plus going to be larger? Li plus and sodium plus. Well, those aren't right next to each other. They're both going to be smaller than their corresponding neutral species, but based on the trend, which one is larger always? Sodium, right? So lithium is still smaller. When we talk about beryllium and magnesium, it's the same thing. Beryllium is right above it, so beryllium is smaller. Li plus and Be2 plus. What is this an example of? What kind of system? I hear people like whispering. Isoelectric, right? These have the same amount of electrons, correct? This is 3 and it loses 1, and this is 4 and it loses 2. So we just want to look at how the protons and electrons are being affected, but we'll see that in this case, lithium plus is larger than beryllium 2 plus. So this is the answer. Lithium would have 3 protons dealing with 2 electrons, and beryllium would have 4 protons dealing with 2 electrons. So this is Be 2 plus, Li plus. This is why this is smaller. There's more strength pulling it in. Right. Speaking of isoelectric, I want to skip this. It's really easy. I'm pretty much just crossing out everywhere it says ground state because we never talk about stuff like that. So how many unpaired electrons are in the calcium atom? That's kind of how we can look at this question. So does anybody know the electron configuration for calcium? What was it? Any unpaired electrons? No. In the case of the nitrogen atom, predict where the greatest jump occurs for successive ionization energies. When does the large jump occur? Well, so just like in a general case, when does a large jump occur for these ionization energies? Like what's happening when that large jump happens? What was that? Yeah, awesome. We're going from those valence electrons into the core electrons, and they become much harder to pull off. So we want to see how many valence there are. How many valence in this? In nitrogen? So there's 5 valence. So it's going to pull off 5, generally easy, and then when it goes to pull off the 6th one, it's going to be really hard, right? So we would see the jump in between what? 5 and 6, yeah. This is weird. So kind of the same thing for GE. So I'm going to change this question up. Instead of how many unpaired electrons, how many valence electrons in the germanium atom? So what is the electron configuration for germanium? Does anyone know? AR? 4s2? 4p? What? 2? Thank you, sorry. What's in the middle of that? 3d10, right? Yeah. Where do our valence electrons come from in this class? Yes, we just consider this. Please don't go looking that up on the internet. You're going to lose your mind. So we pretty much just count 2 plus 2 equals what? HR even? All right. You see where it says HR on this question? It should be HE. Oh, you guys can't even see. It should be HE. Yeah, helium. And then I'm trying to find the last one, SC. SC is in the 21. It has an atomic number of 21. So this has an atomic number of 8. This is 21. This is 18. This is 2, and this is 1. All right. So in other words, this is how many electrons there are. Now argon's what? You guys can't see it. Argon is what? A noble gas, right? So noble gases are they ever paramagnetic? No. So we know argon's going to be diamagnetic. What about helium? Same thing. It's going to be diamagnetic. Calcium. For calcium, we have argon 4s2. Is that di or para? Di. For this SC3+, we have the same thing. It looks like this. Oh, that's wrong. All right, so this is what SC3+ looks like. 21 electrons. But it's 3+, so what do? We take this one away? Or which one will we take away first? The 4s, yeah. So we take this one away, then we take this one away, then we take this one away, and what does it look like? Argon, yeah. So we get rid of that, and the only one left is sulfur. You could also just do sulfur first and see that it was paramagnetic. To each their own. Okay, what this question should say is which of these have the same number of valence? Yeah, some actually. Let's do that. So what is the We're going to just skip this question. It doesn't make any sense when I'm looking at the answer key right here. Just going to avoid that headache. Crossed it out, and then he started talking about it. So I crossed this out. It's about free radicals, and then he went ahead and talked about it today. One of the examples, he was talking about free radicals. So what it says here is that free radicals have an odd number of electrons, and if you remember the free radical he was talking about today in class, it had 11 electrons. So this is saying that the answer is D because NO would have 11, that's the one we did in class, right? Yeah, and then the other one, ClO2, has 19. OCl minus has 14, and N2O has 16. So. In the resonance hybrid or experimentally determined structure of ozone molecule, O3, it is observed that, what is observed by O3? So if I drew O3, what would it look like? How many valence electrons do we have here? 18. 4 in the bonds, there's 14 left. 12 to fill valence, right? And 2 on the oxygen. That's what ozone looks like. 3 electron groups, one of them is a lone pair. What's our shape? Bent. So it looks like that. Octet going on. What's wrong with this picture, though? Yeah, there needs to be a double bond because this oxygen doesn't have its octet, right? So just take one. Oh, crap. So that's what it would look like, right? And so are all of them single bonds? Are all of them double bonds? Was there 20 electrons? The bonds are an so is there one double and the others are single? Can we say that this one bond will always be a double bond? No. Is it more like there's intermediate between double and a single? So this is a situation, I mean, Dr. Hernandez will sometimes talk about this. Those dotted line bonds and Giles, right? Did I say right? This is a case where he was talking about your bond order should be 1.5 because you have kind of like 1.5 bonds because there's resonance going on. So. Yeah, that's what I'll say. Do you guys remember this? So I would imagine that the ACS would kind of ask the way he asked on his last test, where they just like pick out a step and be like, what step is this? That seems really simple. That seems like something you'd be able to answer really quick. This will take you some time if you want to answer it. But I mean, what step is this right here? Let's just talk about them. Sublimation, right? We're going from solid to gas. What step is this? The other one. Not electron affinity. Yeah, this is ionization energy. So here, I'll mark for you. This is sub. What is this? Is this exist? Is this a thing? Or is this a thing? These are the same step, right? Yeah, so. These are different. Usually we dissociate these chlorines, right, before we put them in. So I'm pretty sure this is the wrong step, trying to throw you guys off. This would be our electron affinity step. And this would be our what step? Our delta H formation step. So I don't even think you can determine lattice energy. Yeah, this is wrong. Don't try this. Yeah. If you want practice with this, I would suggest just, if you go to the chapter 9, they do sodium chloride in the book, and you can just follow it along, and that's pretty good. For 25? Oh, I don't know. I didn't do the answer for this. I'm pretty sure because it's messed up. So I said just avoid it. If you want lattice energy practice, go in book. Go in the book. Go in the book, go on his slides. He has sodium chloride, which is easy, magnesium chloride, which is a little bit harder, and then aluminum oxide, which is probably the hardest conceivable question. so given the electronegativities, which single bond has the lowest degree of polarity? So how do we find bond polarity when we're given the values? Subtract. Yeah, you take your delta electronegativity, and we see that the least amount of polarity is between carbon and hydrogen. And this is polar, this is polar, this is polar, and I'm pretty sure this is polar, but this is nonpolar. Another way that if you don't know how to calculate it, but you just know that CH is nonpolar, or if you know that the rest are polar, you would think that, you know, the nonpolar one would have the least degree of polarity since it's not polar. So, yeah. All right. Are we finished out of it? What does isoelectric mean? All right. That's all that's really difficult about that question is understanding that. You just add up electrons pretty much. To that point. Which of the following is are a possible valid Lewis structure for the compound which the molecular formula is C2H6O? Does everybody see this big X right here? That means 1 is incorrect and 2 and 3 are right. Yeah, they pretty much did the work already for us. But, you know, what is wrong with this one? What is wrong with 1? So, okay, but what is very, very wrong with it? The terminal group, yeah. I'm thinking more of this carbon right here. How many bonds are on this carbon? 5. That's like a very, very bad thing when you're making bonds. So, carbon cannot have an expanded octet. It's just wrong for multiple reasons. Someone said the hydrogen in the middle. Carbon cannot have an expanded octet, and that'll also mess with formal charges. So there's like a cascade of things that'll help you understand this is wrong. This is really, putting this here or putting it here doesn't change anything really. So the answer is 2 and 3. So I think this is a really good question. It says which of the following species has an Lewis structure similar to hydronium? So you would have to do hydronium. So that's what it would look like, right? Yeah. So let's find something that also looks like that. Does anybody want to take like a guess which one we should try first? B, yeah, let's try out B first. Yeah. So if you think of hydronium, the things between ammonium and hydronium are exactly the same except for the oxygen and the nitrogen. When you think about the hydronium, it has a positive 1 charge, which means you take an electron away. Oxygen usually has 6 valence electrons. If you take one away, it has 5 valence electrons. Nitrogen has 5 valence electrons, so it should be the same structure. These are ways that outside of Lewis structure you could get the answers just by understanding stuff, honestly, from Chem 1A, making connections and stuff like that. All right, so consider this reaction and calculate the enthalpy. So this is what we're talking about. I can't remember if breaking bonds takes energy or if forming them takes energy. So what do? I grab my pencil. I can't break it because I'm not putting enough energy in. Which means breaking bonds costs energy. So when we look at this, from here to here, what's the difference between this structure and this structure? I'll draw it out. This is a better way to look at it. You should always draw these out. You can see exactly what bond is breaking. And that it wants to become C, H, 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 Cl plus HCl. Do we have to break up this methane at all? Once. What do we want to take off of this? 1 hydrogen, yeah. So we come over here. We remember breaking a bond is positive or negative? Positive, yeah. So positive 414 plus. And then what are we going to want to do? Are we going to want to break this chlorine bond? Yeah, so when we break that, what happens? 243, and it's positive. So at this point, this is what we have. We broke this carbon-hydrogen bond. We broke this chlorine-chlorine bond. That's what's going on. They're kind of floating in space with their, this has 7, that has whatever. Now, we go over the arrow, and to get this bond to form, what do I have to do? Yeah, awesome. So we're going to form a bond between carbon and chlorine, and we're going to form a bond where else? Hydrogen and chlorine. So we find that. And then we just do the math. Did anyone get an answer? Negative 113. So is this reaction, this entire reaction, exothermic or endothermic? Exothermic. That's a great way they could ask this question, is they could have you do this, but these are not the answer choices. The answer choices are literally either A, exothermic, or B, endothermic. That's how I would ask that question. That's how you make it difficult. All right. What is the formal charge on the nitrogen in the nitrate ion? So we have nitrogen plus 3 oxygens equals what? Do we equal 0? So if you guys remember, the sum of the formal charge should equal the charge overall. So in this case, it's going to be negative 1. Sorry. So do we know the formal charge of oxygen? Negative 2. Nice. What's up, man? Yeah. It looks like that. Oh, wow. I'm doing this wrong, aren't I? What am I solving for? This isn't formal charge. This is something else. It's oxidation state. So that's why this is coming out weird. This is this is calculating the oxidation state. So let's go ahead and finish it up because this is part of Chem 1A, Chem 1B, right? So this is not. I'm gonna make a mark. This is oxidation state, which is still important to understand. So we get N equals. This would come out to negative 6, right? So N equals positive 6 minus 1. N equals plus 5, right? This is oxidation state. Yeah, when all these numbers were like plus 1, I was like, I'm doing something wrong. All right, how do we find formal charge? We're going to need to do what first? Draw the structure. How many of you at this point memorize what nitrate looks like? Looks like that, right? Yeah. So, when we think about the formal charge is what? What's the equation for it? Valence electrons minus non-bonding electrons minus bonds. So that's a great question. 1/2 of bonding electron is equal to the number of bonds. So let's think about it. In this structure, let's think about the bonding electrons. There's 4 bonds. How many electrons in a bond? 2. So we have to take 4, multiply by 2 to get 8, which is bonding electrons. Then what do we have to do? divided by 2 to get half of that. What's the easier way to do that? Just 4 bonds. So, is it supposed to be... you did this wrong, Taylor. Let's try this up. So, how many valence electrons in nitrogen? 5. And how many non-bonding? How many bonds? 4. And what does that equal? +1. So remember that nitrogen with 4 bonds is always +1. Oxygen with 2 bonds is always 0. With 3 bonds is plus. With 1 bond is -1. Carbon with 4 bonds is 0. Hydrogen with 1 bond is 0. Stuff like that. Those formal charges that you can just kind of remember. But this was good. We talked about oxidation state. Let's say I meant to do that. And then we also talked about formal charge. It is not -1. It should be +1 because we have 5 valence electrons, 0 non-bonding electrons, and then 4 bonds, or we have 8 bonding electrons divided by 2 is 4. So 5 minus 0 minus 4 is +1. So if you look really closely, you can't see any of that. I kind of saved this one for you on your own. We did ozone earlier, and we already talked about it. It looks like this, and that's this one right there. So the answer is 5. All right, so this is what I was talking about. Which molecule has the largest dipole moment? Hydrogen to fluorine. What's up, man? Oh, yeah. Hydrogen and fluorine, right? And that's just because, fluorine is the most electronegative, so it's just going to have the largest polarity, largest dipole moment. All right. If one atom is replaced with a lone pair of electrons, from which fundamental geometry below could you create a molecule having trigonal pyramidal shape? So I have X amount of electron groups. I take one, they're all bonds at this point. I take one bond away and I give it a lone pair, and now my molecular geometry is trigonal planar. What electron geometry am I dealing with? Tetrahedral, nice. If your electron geometry is tetrahedral and one of those electron groups is a lone pair, your molecular geometry will be trigonal pyramidal. Which molecule below is non-polar? So we did sulfur tetrachloride. Will that be any different than sulfur tetrafluoride? No, it's sulfur bonded to 4 halogens. Everything's going to donate the same amount of electrons, and everything's going to have generally the same pull on polarity. So we saw sulfur tetrachloride was polar, so we can assume that sulfur tetrafluoride will also be polar, right? OF2, that's going to look something like something that we need to survive. It's going to look like this, but with fluorines. And then we could say that, will this be polar or non-polar? Polar, yeah. pH3. What is right above P on the periodic table? Nitrogen. What does NH3 look like? It's trigonal pyramidal. Yeah, so NH3 look like this. So pH3 should look exactly the same. Everyone's donating the same amount of electrons. Polarity is going to be generally the same. We said NH3 was polar, so we have to say pH3 is polar, right? CBrCl3. This one's good. Now, this is going to look almost like carbon tetrachloride, which we did earlier. What's the difference between this and carbon tetrachloride? Yeah, there's a Br. It's not equal magnitudes all the way around. So when we have a tetrahedral shape with equal magnitude of polarity on the bonds, it's usually nonpolar. But since these two will cancel out and these won't, since they have different magnitude of polarity, this structure will be polar, right? Yeah. And then you come to this, and I'm almost 100% sure this looks is linear. Let's find it. Yeah. This is what this looks like. So Xe, or xenon tetrachloride, has 4 extra electrons around the central atom. That gives us 6 electron groups, and that gives us a molecular geometry of square planar. If everything's equal magnitude and your molecular geometry is square planar, will your structure be polar? No. Everything's going to cancel out. It's all in the same plane. It's pretty much like, it'll literally look like that. These chlorines will be on the same plane, and this guy will cancel out with this guy, and this guy will cancel out with this guy, and they'll be nonpolar. So you want to be sure that you're not looking at, OF2 like this. This is 2D. This is 3D. In 2D, it's nonpolar. In 3D, it is polar. What is life? 3D. So consider actual life when you take these tests. Imagine if life was 2D. That would suck. All right. Which molecule has a lone pair? That's not too deep, but I want to do this one. So we have CF. So what is it? It's carbon with 4 halogens. So it's really anything in a change. We can look at it once again like it's carbon tetrachloride. Halogens will donate the same amount of electrons as another halogen. They all have 7 valence. And carbon is carbon is carbon. So when we look at this, what is true? Is this going to be polar? So remember, and this will become clear when you guys, if you check out that table 10.2, tetrahedrals are nonpolar only if everything has equal magnitude. So when you look at this, do these bonds have equal magnitude of polarity? No. And I know the way I drew it, it looks like, oh, the top one's going to cancel out with the bottom one, and the left one's going to cancel out with the right one. But we know that these tetrahedral structures, they're in 3D. They're not just sitting, lying on the ground, separated by 90 degrees. That would be square planar. This is tetrahedral. It's almost like a tripod with a big stick coming out of it. So they need to all be the same magnitude, so when they pull in separate directions that are equal, they all cancel out. But if that's not the case, two directions will get pulled a little more than the other 2 directions, and that's all will have polarity. It'll look different. So the statement is actually this molecule is always polar. The I's will not cancel out with the F's evenly, and there will always be polarity towards the fluorines. The only way a structure like this could be nonpolar is if we had like this, CF4I2. And what we would see is we would have F, 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 and then I. Now, the geometry of this is octahedral. Now, this is where everything is. There's 2 different planes. We have that square planar plane, which is, a bond coming out of my stomach, my two arms and a bond coming out of my back, and then we have these iodines, which are on the top and bottom, so like my head and my feet. Well, when we look at that, the iodine will cancel out with the iodine. That makes sense. And then those fluorines will cancel out with each other, and this will be nonpolar. But this is polar because you can't get a way to get them all to line up on a plane without being, like this iodine could never be in the structure and, not also be dealing with the fluorine. So I thought this was a good one because we don't see a lot of these where it's two halogens and two different halogens. Okay, so based on the molecular orbital theory, the bond order of an H2 molecule is what? So what orbital do we only consider for hydrogen? Yeah, the 1s orbital. So we have 1s anti, 1s bonding. And this hydrogen has one electron, this hydrogen has one electron, they both go in here. What's our equation to find bond order? So bonding minus anti-bonding divided by 2 equals 1. All right, cool. So ethylene looks like this. Oh, ethene. All right, so if you drew it out, you would see that there's a triple bond in between the carbons. One day you'll learn that that's what those last three letters actually mean. So when we look at this, what type of orbitals overlap to form each carbon, hydrogen, sigma bond in ethene? So this carbon has what kind of hybridization? sp. And then, let's see, hydrogen is just in the 1s orbital. This is a weird question. I would have skipped it if I saw it. But pretty much what's important is, think about this. What is the hybridization of the carbon? sp. That's kind of where you guys are focused on. All right, I like this. All right, so we're going to have to draw this, right? This is my assumption on what it's going to look like. Got an ether. All right, so 4 plus 4 is 8 plus 6. Or how about 4 plus 6 is 10 plus 4 is 14. 1, 2, 3, 4, 5, 6. 20. 1, 2, 3, 4, 5, 6, 7, 8. 16. 4 left. Did everyone kind of get something like that? Oxygen in the middle. So how many pi bonds? 0. How many sigma bonds? Yeah. So awesome. Yeah, that's pretty easy. That's how you can get asked that. How many sigma and pi bonds in this structure? So you have to draw it correctly and then count the sigma and pi bonds. Predict the molecular geometry about the nitrogen atom in the molecule that. So, once again, we're going to have to draw this. CH3 and H. So, we do the same thing. We have 8 coming from these carbons plus 5 coming from the nitrogen. That's 13 plus 1, 2, 3, 4, 5, 6, 7. That's 20 minus 2, 4, 6, 8, 10, 12, 14, 16, 18. That leaves 2, and those are going to go right here, right? What is the molecular geometry of this nitrogen? That's hard to see, sorry. It's going to be trigonal pyramidal. 4 electron groups, 1 lone pair, trigonal pyramidal. And what about these 2 carbons? Tetrahedral, yeah. What about these ones? All right, so this is what I was talking about. What is a saturated hydrocarbon? You shouldn't know that. If you do, awesome. Stuff like this. All right. All right, so this one right here, number 53, it's a gas law question. It says, what gas sample has the greatest volume at STP? So we want to find volume. So we know that we first have to do what? We have to convert these to moles, right? Yeah. How'd you do this? Oh, okay. I'm sorry, I get it. All right, so we see that we have 5 grams of each substance. And we know, what is molar volume at STP for a gas? 22.4 liters. So 1 mole of gas is 22.4 liters. Are these moles? No. If we turn them into moles, we'll have different values. And since 22.4 is a constant that we're just going to be multiplying these numbers by, what would we want these values to look like to get the greatest volume? What would we want? The largest amount of moles or the least amount of moles? Largest amount of moles. And so we want largest amount of moles. Largest amount of moles gives us largest volume. But when we're going from grams to moles, we put molar mass on the bottom, right? So if your molar mass is larger, will you yield more or less moles? Less moles. But that's not what we want. We want largest moles. So we're looking for something that's really light, correct? So small molar mass equals large amount of moles equals large volume. So which one of these has the smallest molar mass? What was that? Someone say C? Yeah, neon. How many of you saw this problem and immediately felt the need to start like working stuff out and doing all this math and stuff like that? Yeah. So if anybody felt like that, there's ways to look at this. If you understand your concepts, if you understand what's happening with the stoichiometry, there's ways around all this math doing, for us to convert all those into moles and then look at it would be 5 minutes wasted, but for you to convert all of them into moles and then convert all of them into volume, that's like 10 minutes of wasted time, depending on how you do your math, if you make sure you check all your calculations and stuff like that. So know your concepts, they'll help you out. All right, and I think we're going to have to finish up on this one. I think these two are pretty important. This is a partial pressure question. Who remembers how to do partial pressure? Good, one person. I'm glad I'm doing this. So, I remember partial credit. Okay, so the way this starts is it says 39.8% nitrogen by mass. What does that mean to us? When we see percent, what do we immediately think? I'm sorry? No, you said it right. Yeah, you want to assume 100. So if we have 39.8% nitrogen by mass, and we're assuming 100, we have 39.8 grams of nitrogen by mass, or nitrogen. How do we remember what our diatomic molecules are? You guys remember that? Yeah, so what is it? Have no fear of ice cold beverages. I'll try to be academic today. Or all the time. I'm academic all the time. What's the first one? Hydrogen, nitrogen, fluorine, oxygen, iodine. What is this? Chlorine? Bromine? So yeah, that's how you remember that. Because for questions like this, let's say they don't say O2 and N2 at the beginning, you need to know that nitrogen gas is N2 and oxygen gas is O2. They'll throw off your mole, whatever, your mole calculations. So 1 mole is 28 grams, and that equals 1.42 moles. And then if we assumed 100, and out of that 100, 39.8 is nitrogen gas, how much is oxygen? Yeah, the rest. So 100 minus 38, or 39.8, and then you get what, 60.2 grams O2? 1 mole is 32 grams. That equals 1.88 moles. So what are we trying to find in these partial pressure questions? We want to find the mole fraction, right? And then once we get the mole fraction, we can multiply that times the total pressure, and that'll give us our partial pressure. If you want to think of it as, no, don't think of it like that. All right. So they're asking us for the partial pressure of oxygen. So the mole fraction of oxygen is equal to what? How do you find mole fraction? Same way you find mass percent composition, like this step. Yeah, moles of oxygen over moles of everything, right? Thank you, Pierre. You're going to do moles of oxygen, which we calculated as 1.88, and divided by moles of everything, which is these two added up, 3.33. And what you get is you get a partial pressure of, a mole fraction of oxygen to be 0.57. Well, we go back to the problem. It says 505 millimeters of mercury. So to find the partial pressure of O2, we will be doing 0.57 times 505, and that equals 287.7, or 288 millimeters of mercury. Pierre, are you back there? Am I supposed to tell him anything about the survey? No one said anything there. Where is it? Oh, okay. All right, so kind of wrapping up. I know it should end at like 7:20, 7:25, so I'm trying to save 10 minutes if anybody has questions they want to ask me, one-on-one, or if you want to come take pictures of this. On the edge of the table, if you have the QR code and you can just scan that and take the survey, or if you don't mind typing in the link and just filling out the survey, it helps us with funding, letting us know if we're making progress. If I should have my, no, I'm kidding. That won't determine my job, but it really helps us out. It lets us know where we're doing good and where we're doing bad, and how we can just make SI better for you guys next semester. If you came out to any review sessions, any SI sessions, and I helped you even answer one question that you couldn't answer, I'm glad I could help. I hope you didn't come out all semester and I didn't help. That would be sucky, but thank you. This is my last time doing Chem 1B, so I hope you guys do really good, and we can all end on a good note, and everyone can go to Chem 2, and we can stress out about other chemistry. But yeah, so if you have questions, just come up here. I'm going to take the mic off. What happened? No, I'm not. I'm doing organic one. Oh, and to those of you that came to like every SI session, you guys are awesome. This was probably the semester where I knew the most people by their first name, and you guys are really cool. You made my job not horrible, so thank you.